So we will jump into the presentation as early as possible. So my name is, am I audible to all? I hope so.
Yes, I can hear you.
Yeah, all right, okay. So, so again, extremely sorry for the delay. And so today the topic was actually for transport of oxygen and carbon dioxide. I wanted to make it as a didactic topic plus MOOC Viva. But then the last moment I just decided to do a presentation. But of course, if anyone is interested to discuss it at the end, of course, I can leave some session, because the most important thing is, I think, our Viva preparation. So it will be much better if it will be an interactive session. And if anyone wants to join in and add more points, or want to, discuss about this topic in detail, most welcome. So I will just go through the topic in the first 20 or 30 minutes or so, and the rest we can take it from there further. Okay, so so the transport of oxygen and carbon dioxide is one of most important topic in the European Diploma of Anesthesia and Intensive Care Examination. I think pretty much 50, more than 60-70% people in one of their stations, they do go through these topics. The examiners are fond of asking it. Of course, it's one of the basics the anesthetist has to know about. So now coming to the topic, transport of oxygen. Oxygen transportation from the lungs to the cells of the of tissues. So basically that is all what we are looking forward to. So starting from the ventilation of the lungs allows atmospheric air into the lungs, and this supplies the oxygen to the alveolus. Diffusion of the oxygen across the alveoli capillary membrane into the blood and carried as dissolved in plasma and combined with hemoglobin. So as you all know, that the major portion of the oxygen is combined with hemoglobin, and a very, very minute part is dissolved in the plasma. And finally, the diffusion from the capillary into the cells and further into the mitochondria. So this is just a summary. The oxygen is carried in blood in two forms. One is bound to hemoglobin, which is 97 to 98%, and then the oxygen dissolved in plasma. Now, the oxygen dissolved in plasma, it follows the Henry's law. The amount of gas dissolved in a solution is directly proportional to the partial pressure of oxygen. So this same principle is the one which actually we use for the hyperbaric oxygen therapy in certain conditions, like I think for burns management and all now we use. So that is one way of increasing the level of oxygen. So increasing the partial pressure of oxygen and increasing the dissolved amount of oxygen in the blood. Now, just want to go through the detail about hemoglobin. Hemoglobin is a tetramer containing 4 subunits, and each subunit has a glycopeptide chain. I'm sorry. Okay, there's a disturbance going on. Okay. So hemoglobin is a tetramer consisting of 4 subunits, and each subunit has a glycopeptide chain in association with a heme group. Heme is a compound of iron and porphyrin, which is an essential part of the oxygen binding sites. Only the divalent form of iron can bind the oxygen. In normal adults, 98% of the hemoglobin molecule consists of 2 alpha and 2 beta chains. The remaining 2% is in the form of HbA2. The 4 subunits are held together by weak bonds between the amino acid residues. Each gram of hemoglobin can theoretically carry up to 1.34 ml of oxygen. Oxygen binds to the ferrous ion in hemoglobin by forming a reversible bond. There is no oxidative reaction, and so the iron atom always remains in the same ferrous form. Each molecule of hemoglobin can bind 4 molecules of oxygen, and there are several factors that influence binding elaborated with the oxygen dissociation curve. Dissolved oxygen represents a small fraction of total oxygen carrying capacity of the blood. It still constitutes an important fraction. The dissolved fraction of oxygen is also responsible for triggering the hypoxic respiratory drive. That's another topic which I'm not covering in this, but very important for the Viva. Oxygen hemoglobin dissociation curve. So as you all know, it's a very, very important topic. So the oxygen hemoglobin dissociation curve is a graph relating the percentage of oxygen saturated with oxygen to the partial pressure of oxygen. Arterial PO2 is around 100 millimeters of mercury with a hemoglobin saturation of 97%. And venous PO2 is around 40 millimeters of mercury with a hemoglobin saturation of 75%. And the P50 is around 26 millimeters of mercury. So P50 is the PO2 at which the 50% saturated hemoglobin is saturated with oxygen. The oxyhemoglobin dissociation curve has a typical pattern, an S-shaped pattern, and the reason for this S-shaped pattern are due to two things. The one is the allosteric modulation, where the oxygen binds to the hemoglobin with two beta chains, which move closer together and change the position of the heme moieties that assume a relaxed or the R state. When oxygen dissociates from hemoglobin, the reverse happens and the heme moieties take up a tense or the P state. And the second one is the cooperative binding, where the oxygen binds to the hemoglobin. The R state is favored, which has an increased affinity for oxygen and so facilitate the uptake of additional oxygen. The affinity for oxygen for the fourth oxygen molecule, that is therefore much greater than for the first one. So basically, as it gets joined, the last one joins much easier, and that's why the curve it goes as a S shape. Now there are the factors which influence the oxygen dissociation curve. So one is which shifts the oxygen dissociation curve to the right, and one which shifts to the left. And the factors which shift the oxygen dissociation curve to the right are the acidosis, that is low pH, increase in, that is hypothermia, increase in temperature, increase in 2,3-DPG, which is a phosphate byproduct, as you all know, increase in the PaCO2 or hypercarbium, anemia, pregnancy, post-acclimatization to altitude. And the factors which shift the ODC to the left are the high pH or alkalosis, low temperature, low 2,3-DPG, low PaCO2, fetal hemoglobin, which contains of 2 alpha and 2 delta subunits, methemoglobin, carboxyhemoglobin, and stored blood. Now, 3 points I have given there. One is Bohr effect, double Bohr effect, and Haldane effect. I am coming into it further into my presentation. So these are the 2-3 things they might ask when we discuss about ODC curve. So these are the 3 topics they can go into. One is a Bohr effect. They can ask what is double Bohr effect and what is Haldane effect. So now coming to the oxygen content. The oxygen content in blood in 2 main ways. It is carried in blood in 2 main ways. One is, as I told earlier, combined with hemoglobin or dissolved in plasma. Now, the oxygen content is calculated by combining the proportion of both bound in hemoglobin as well as dissolved in plasma. So the formula goes as hemoglobin into saturation of oxygen into 1.34 plus the partial pressure of oxygen into 0.003. Now 0.003 ml of oxygen per deciliter of blood per millimeters of mercury of oxygen partial pressure. 1.34 is the Huffner's constant. Sorry, I think somebody.
The rest of the people, please mute their microphones, please.
Yeah, please. Thank you. So 1.34 is the Huffner's constant. Each gram of hemoglobin combines with 1.34 ml of oxygen. And SaO2 is the saturation, and PaO2 is the partial pressure of the arterial oxygen. So this formula, we will have to actually write it down over there, and we have to explain each part of the equation to the examiner. So another one thing I just want to add up, whatever they ask, if there is a chance for us to illustrate or to write down something, it will be much better. It will be an advantage in the Viva if we can illustrate or write it down to the examiners. Now, arterial oxygen content, or CaO2, as I showed before the equation. Now, in a normal individual for like HB of 15, you can equate and see how much the arterial oxygen will be using this formula. The same formula applies to the venous oxygen as well. The oxygen transport is dependent on both respiratory and the circulatory function. So total oxygen delivery to the tissue is the product of the oxygen content and the cardiac output. The arterial oxygen content is dependent on the partial pressure of oxygen and the hemoglobin concentration. The deficiency in the oxygen delivery may be due to low partial pressure of oxygen, low hemoglobin concentration, or an inadequate cardiac output. So the normal oxygen delivery can be calculated as 20 ml oxygen per deciliter of blood into 50 deciliter of blood per minute is equal to 1000 ml of oxygen per minute. The Fick's equation expresses the relationship between the oxygen consumption, oxygen content, and the cardiac output. The oxygen consumption, when it comes to the VO2, the VO2 is the product of cardiac output and the difference between the arterial oxygen content and the venous oxygen content. So that is the oxygen consumption at the tissue level. The arteriovenous difference is a good measure of overall adequacy of oxygen delivery. The arteriovenous difference is about 5 ml oxygen per deciliter. The normal extraction fraction is about 5 ml, that is 25% of what goes to the tissue. So thus the body normally consumes only 25% of the oxygen carried on hemoglobin. When the oxygen demand exceeds supply, the extraction fraction exceeds 25%. Conversely, if oxygen supply exceeds demand, the extraction fraction falls below 25%. So, okay. So when further reductions happen, a critical point. So, when the delivery of oxygen delivery even moderately is reduced, the oxygen consumption usually remains normal because of increased oxygen extraction. Mixed venous oxygen saturation decreases and the oxygen consumption remains independent of delivery. But there is a point at which it becomes proportionate to the delivery of oxygen. That is, once it reaches a critical point where the state of the supply dependent oxygen is typically associated with progressive lactic acidosis caused by cellular hypoxia. Now, what are the factors that affect the oxygen extraction? Now, extraction can be increased with decreased cardiac output, increased in oxygen consumption. Third is exercise. Fourth in seizures. Fifth in shivering. Sixth in hypothermia and anemia and low PaO2. So these are very important aspects, especially for the anesthetist, because these are the things we are supposed to avoid to avoid hypoxia. And then extraction is decreased with increased cardiac output, skeletal muscle relaxation, peripheral shunting, hypothermia, increased hemoglobin, and increased partial pressure of oxygen. When oxygen consumption is high, increased oxygen requirement is provided by increased cardiac output. Alternatively, if the oxygen delivery falls, relative consumption, tissue extract more oxygen from the hemoglobin. Now, coming to an important topic, that is the oxygen cascade. So when we talk about the transport of oxygen, the main thing is the oxygen cascade, which shows the pathway from the atmospheric oxygen through our lungs all the way till the mitochondrial level. So the pathway of oxygen from the atmosphere all the way till the mitochondria is the oxygen cascade. We will have to draw the actual diagram and label it. It will be much better if we can do that and then explain the oxygen cascade. So oxygen is present in the air at a concentration of 21%. Atmospheric pressure at sea level is around 760 millimeters of mercury. Now, inspired partial pressure of oxygen at sea level is therefore around 157 millimeters of mercury, which is that 21% of atmospheric pressure. Now, humidification of air, which happens in the upper airway tract. So we have to consider the saturated vapor pressure, which is around 47 millimeters of mercury. So subtracting the 760, which is atmospheric pressure, minus the 47 of the saturated vapor pressure into the oxygen concentration, that is 21%, which comes around 149 millimeters of mercury, which is being inspired in the upper airway tract. By the time the oxygen reaches the alveoli, the partial pressure of oxygen has fallen to around 112 millimeters of mercury. This is because it balances between the removal of oxygen from the pulmonary capillaries and also the adding up of the carbon dioxide. So because of this balance that happens, it decreases from 149 to 112 millimeters of mercury. Now, the blood returning to the heart from the tissues has a very low partial pressure of oxygen, that is around 40 millimeters of mercury, and it travels to the lungs via the pulmonary arteries. The pulmonary arteries form the pulmonary capillaries, which surround the alveoli, and the oxygen diffuses from the high pressure in the alveoli to the area of low pressure of blood in the pulmonary capillaries. After the oxygenation, blood moves into the pulmonary veins, which return to the left side of the heart, which pumps the blood into the systemic tissues. In a perfect lung, the partial pressure of oxygen of pulmonary venous blood would be equal to the partial pressure of oxygen in the alveolus. But this is not. And the reason for that is three factors which may cause the partial pressure of oxygen in the pulmonary veins to be less than the alveolar partial pressure of oxygen. That is, one is ventilation perfusion mismatch, second is shunt, and third is diffusion impairment. So these are the three factors which causes the disparity between the alveolar partial pressure of oxygen and the partial pressure of oxygen in the blood which reaches the left side of the heart. Arterial blood with a PaO2 of 100 millimeters of mercury passes to the tissues. The capillary PaO2 being in the order of around 45 to 52 millimeters of mercury. Oxygen then diffuses into the cell in the capillary beds. The mitochondria receiving a PaO2 of between 7.5 to 37.5 millimeters of mercury, depending on the capillary bed. An increase in the size of any of the steps in the oxygen cascade may result in hypoxia at the mitochondrial level. Only 1 to 3 millimeters of mercury is actually required for the chemical process. And so at this point, one important question that can come is the question about the Pasteur point. Pasteur point is nothing but a critical mitochondrial PaO2, partial pressure of oxygen, below which the aerobic metabolism is impossible. In normal individuals, the alveolar arterial gradient is less than 2 kilopascals and is caused by small ventilation perfusion mismatch and shunt present in a normal healthy adults. Okay. As an increase in the alveolar arterial gradient occurs in disease states that cause an increase in ventilation perfusion mismatch or shunt or conditions which impair diffusion. Diffusion impairment occurs in disease states like pulmonary edema or pulmonary fibrosis. Shunt, one cause is the intrapulmonary causes and the extrapulmonary. Intrapulmonary causes are lower respiratory tract infection or atelectasis, and the extrapulmonary causes are right to left cardiac shunt. And the ventilation perfusion mismatch due to the infections, asthma, COPD, and hypotension. So there I have given a summary of the oxygen cascade. So we have to remember the atmospheric air, the 21% of oxygen, partial pressure of oxygen of 159, which comes to the upper airway tract, gets diluted by the water vapor, goes to 149 millimeters of mercury, diluted by carbon dioxide, and the partial pressure of oxygen comes to 99 millimeters of mercury at the alveolar level. Also, some oxygen is taken up by the capillaries, which decreases the alveolar PaO2. N-capillary blood, essentially the same as alveolar gas in healthy patients. Arterial blood diluted by the venous admixture, PaO2 of 92 millimeters of mercury. The difference between the alveolar and the arterial gas is the A gradient. Normal A gradient is 7 millimeters of mercury in young and 14 in the old. Now, finally, at the mitochondrial oxygen level, it comes down to around, as I told, usually between 1 to 10 millimeters of mercury. Okay, now coming to the second part of the topic, that is the carbon dioxide transport. Now, carbon dioxide under resting conditions, carbon dioxide production in the body is approximately 200 ml per minute, and the carbon dioxide formed in the cells diffuses through the interstitial space to enter the venous circulation. The carbon dioxide is transported in the blood in three forms. 5% of the carbon dioxide is dissolved in blood, carbon dioxide being 20 times more soluble than the oxygen. 5% of the carbon dioxide is transported as carbamino compounds, that is attached to the hemoglobin, the NH2 group of the hemoglobin, and 90% as bicarbonate, mainly in the plasma. So the dissolved carbon dioxide first, which is more soluble, so carbon dioxide which is more soluble in the blood than oxygen, with a solubility coefficient of 0.031 millimoles per liter per millimeters of mercury, that is 0.067 ml per deciliter per millimeters of mercury at 37 degrees Celsius. Second is the bicarbonate, which forms the 90% of the carbon dioxide transport. So carbon dioxide, which slowly combines with water to form carbonic acid in aqueous solutions, and the bicarbonate, according to the following reaction, that is carbon dioxide plus water forms carbonic acid, and this again gives out hydrogen ions and a bicarbonate. In plasma, although less than 1% of the dissolved carbon dioxide undergoes this reaction, the presence of the enzyme carbonic anhydrase within the red blood cells and endothelium greatly accelerates the reaction. As a result, bicarbonate represents the largest fraction of the carbon dioxide in blood. The bicarbonate formed in the above reaction diffuses out of the red blood cells. However, the accompanying hydrogen ions cannot follow due to the relative impermeability of the red blood membrane to such cations. In order to maintain electrical neutrality, the chloride ions diffuse into the red cells, and this process is called as the chloride shift. This is another topic they can ask about. And we will have to, there's a diagram which unfortunately I was not able to get it. So we have to actually draw and show the pathway. The Haldane effect describes how carbon dioxide transport is affected by the state of the oxygenation of the hemoglobin. This is because the deoxyhemoglobin is better than oxyhemoglobin in combining with carbon dioxide to form carbamino compounds. In turn, okay. I was talking about the Haldane effect, which so in that, so the deoxyhemoglobin, deoxyhemoglobin combines with carbon dioxide to form carbamino compounds, and it combines with hydrogen ions, in turn assisting the blood to load more carbon dioxide from the tissues. As carbon dioxide leaves the tissue cells and enters the red blood cells, it causes more oxygen to dissociate from the hemoglobin. And the more carbon dioxide combines with the hemoglobin, and more bicarbonate is produced. Hemoglobin acts as a buffer and accounts for the part of the Haldane effect. It can act as a buffer when at a physiological pH because of the high content of histidine. The acid-base behavior of the hemoglobin is influenced by its oxygenation state. Removal of oxygen from the hemoglobin in tissue capillaries causes the hemoglobin molecule to behave more like a base. By taking up the hydrogen ions, hemoglobin shifts the carbon dioxide bicarbonate equilibrium in favor of greater bicarbonate formation. Deoxyhemoglobin also increases the amount of carbon dioxide that is carried in venous blood as bicarbonate. As carbon dioxide is taken up from the tissue and converted to bicarbonate, the total carbon dioxide content of blood increases. In the lungs, oxygenation of hemoglobin makes it behave as an acid, and the release of hydrogen ions shifts the equilibrium in favor of greater carbon dioxide formation. So bicarbonate concentration decreases as carbon dioxide is formed and eliminated. So the total carbon dioxide content of blood decreases in the lungs. And 5% of carbon dioxide, apart from the other two methods, is transported as carbamino compounds. So carbamino compounds are carbon dioxide which can react with amino groups or proteins. At physiological pH, only a small amount of carbon dioxide is carried in this form, around 5% as carboamino hemoglobin. Deoxygenated hemoglobin has a greater affinity, around 3.5 times for the carbon dioxide than does the oxyhemoglobin. The venous blood carries more carbon dioxide than does arterial blood. So that is again the Haldane effect. The PCO2 normally has little effect on the fraction of carbon dioxide carried as carbamino hemoglobin. Now coming to carbon dioxide dissociation curve. So definitely they will ask us to draw and explain about it. So it is a chart which is plotted by the blood carbon dioxide content is plotted against the partial pressure of carbon dioxide, and which shows the three forms of carbon dioxide being transported. One is the dissolved one, the bicarbonate, and the one which is attached to the hemoglobin. So the total carbon dioxide carriage in blood depends on three parameters. One is the partial pressure of carbon dioxide. The other one is the plasma pH level, and then the partial pressure of oxygen. The carbon dioxide dissociation curve relates the partial pressure of carbon dioxide to the amount of carbon dioxide carried in the blood. So lower the saturation of hemoglobin with oxygen, larger the carbon dioxide concentration for a given PaCO2, and the CO2 curve will be shifted to the right by increasing SpO2. Carbon dioxide content rises throughout the increase in partial pressure. Carbon dioxide dissociation curve is more linear than the oxygen dissociation curve. So this is all with the presentation which I have to. So I'm just stopping the share. Okay. So okay. So basically, the topics they can ask for the exam in particular, one will be the oxygen dissociation curve. So this was one question which they have asked many students. I mean, exam, the people who have attended the exam, and and another one was the oxygen cascade and the carbon dioxide dissociation curve. Okay. Anyone, any points to be added, please?
Can I say a word about it, sir?
Yes, please.
If this entire mechanism of carbon dioxide getting converted to bicarbonate and then being transported to the pulmonary capillaries and then again converted to carbon dioxide is possibly because carbon dioxide has a higher affinity for oxygen. Sorry, hemoglobin has a higher affinity for carbon dioxide than oxygen. And if this mechanism was not involved, it would be very difficult for the oxygen to combine with hemoglobin in the pulmonary capillaries.
Yes, exactly. Yeah.
And so there's probably an antiport also, which acts in the extrusion of bicarbonate out of the RBCs.
Okay.
And there was one parameter I read somewhere that normally oxygen delivery to the tissues is flow independent.
In the tissue level,
yes. And it becomes flow dependent after 56% saturation.
Yeah. So
except for the
that is one
circulation.
point I have covered, the extraction of oxygen at the tissue level. It is only So it is not flow dependent. Yeah, true.
But after saturation falls below 56%, it becomes
directly proportionate to the flow of the oxygen. Yeah.
Yes, sir.
Okay.
So can we have this text which was being displayed? Can we have a copy of it?
Yeah, I can send it in the GAN group. I can. Yeah,
that would be great.
Yeah, and
excellent, sir. You have covered everything very nicely, and
so I'm sorry. I wanted to make it a mock as well, so that you guys can. It's actually it is. I know that all of you know more, even more than this. But the point is, we need to conduct more mock vivas so that you guys can practice before going for the actual exam. So from my next topic onwards, I will be doing it as a mock viva rather than as a didactic session, because I think these basic topics we don't need it as a didactic section because everyone will be reading about all this. It is just an area should be given so that you guys can speak out and because.
Yes,
yeah, most of the consultants will be working for long, so will be away from the actual vivas for a long time.
Now I have one more query.
Yeah, please.
Like the entire topic cannot be told in the viva.
Yes,
because it will take too long and there are other questions to ask.
Yeah.
So actually, what fraction of this is expected to be asked of one candidate?
Yeah, so that's what I wanted to say. In EDAIC, actually, they start with a topic and then they lead us to another one, and then we go in that way. That's why if you have noticed, I had pointed out 3 points: the Bohr effect, the double Bohr effect, and the Haldane, while I was talking about the transport of oxygen. So those are the 3 lead questions where they can go in while asking the viva. So that's how they take us, they walk us through. So and given for one examiner, I think it was when I had given in 2018, it was 12.5 minutes per session. So 2 examiners together.
Even now, sir. And how many questions does one examiner ask?
So it depends. For me, it was one examiner had asked around 4 or 5. So one person he started with cardiac cycle and he finished with hyperkalemia. So the spectrum, it's it can go from.
If we have 12.5 minutes to answer 4 or 5 questions, first question maybe we can speak for 4 or 5 minutes. After that, a minute or 2 each.
Yeah.
Some time would be required by the examiner also while asking questions.
Yes. And try to illustrate whatever possible, like graph if there is any equations. just that's why I have given some equations. I have tried to include it as much as I can, but I wanted to include that that chloride shift, that diagram as well. But I don't, technically I'm very not that great, so that's why I couldn't do that. But that so those kind of equations are very important. So wherever possible, we have to include that.
So can we keep graph paper also with us during the examination?
I'm not sure about it. I'm not exactly sure about it.
The instructions say that we can keep paper and black pen.
That's all. Just a white paper and
white
pen.
paper.
Yeah.
But then drawing a graph, blank graph, not a drawn graph.
No, they rather than the precision, they just want to know what informations you can show it in, illustrate in that graph.
Can we keep a scale also?
I don't know the right now, because
drawing straight line with free hand is difficult.
I know, but they just want us to know. See, they just want to know. Do we have the information about the graph? That's all. So don't have to worry about the scale. Or
I mean, scale and like that's what I was thinking. I'm not good at drawing, so I may not be able to draw a graph without having a guidance of graph.
No, but even if it looks awkward, they just want to see if you have labeled the correct informations, and that will fetch you the highest marks. So don't worry about it. Yeah.
So one question I have, not related to the exam as such. If somebody who's hoping to work in UK after this exam, is there any upper age limit for joining NHS?
I am not sure. I don't know. No idea. I think the consultants in UK should. I have worked in UK, but I am not. I have worked in a staff grade position, so I am not. I am not sure about it.
Great, sir.
Thank you.
You have actually summarized in a very short time. You have packed in everything, and you have also
sorry
by
to keep
filtering
you guys
out information which we probably don't need.
Yeah.
What I am finding is more of a challenge to weed out what we don't need.
I know. So yeah. So we have to basically go through almost all the topics, but not in an extremely detailed way. But we should be knowing it, at least the basics of the things. Yeah, that's what they expect us to do. Yeah.
Sir, I have a doubt.
Please.
Sir, which unit do they prefer for pressure? MMF HG or KPA?
So I when I gave my exam, I gave it in millimeters of mercury. So I just followed the millimeters of mercury because I didn't want to introduce a new thing over there, and I will rather get confused. So I just went with the millimeters of mercury. Yeah.
I also plan to use millimeter mercury because
yes,
all my life
I think there is absolutely no issue like that. So they will accept it. Yeah.
Thank you, sir.
Thank you.
Thank you, sir.
So, okay. So I think we can stop the session so next time, hopefully we can have a Viva as well. So
great.
Okay.
Waiting for it.
Thank you very much.
Thank you.
Thank you, Doctor.
Thank you.